Good afternoon, everyone, and welcome to today's sponsored ABC webinar, Biogas Desulfurization Experiences with Thiopaq Scrubbers. My name is Caroline Pete, and I will be facilitating this webinar. Before we begin, I want to thank Paques for sponsoring today's webinar. Their sponsorship directly supports the ABC and our programs. So thank you so much to our speakers, Andrew Delgado and Martin Thiopaq, for your whole team at Paques for this partnership. We really appreciate this. Before we begin, I just want to go through a few housekeeping items. You should already be able to hear me and see the slide that is titled Quick Notes. If you're hearing echoes or your sound quality is bad, you can change the audio options in the GoToWebinar toolbar, which is usually on the right side of your screen. There's a pod, it's called audio. If you're still having trouble, you can send the organizers a message using the questions section of the toolbar. And don't worry, we are also recording this webinar. The slides and the recording will be sent to you in a few days by Friday at the latest. If you have any questions during the presentation, you can ask those at any time, also using that questions pod in the toolbar. We'll handle all the questions at the end of today's presentation. It's great to see that we have so many ABC members on the line. I want to thank you for your continued support to make all that we do possible. For those of you who aren't yet members, we're also thrilled to have you with us as well. In case you're not familiar with the American Biogas Council, we are the voice of the U.S. biogas industry. We represent about 220 organizations, which reflect the entire American biogas industry. And if you're not a member and you'd like to engage with us and help grow the biogas industry and your business, please email us through our website. It's americanbiogascouncil.org. So I'm going to thank you all for joining us again, and I'm going to hand things off to our moderator, Executive Director of the American Biogas Council, Patrick Surface, to lead you through the great presentation we have for you today. Patrick, please take it away.
Hi, everyone. Thank you so much, Caroline. Really appreciate you pulling this all together for us. She does all of our events and does a great job, and we're especially excited to have our friends at Paques pulling together this webinar for us and featuring their Thiopaq technology. You know, we were talking about this a little bit yesterday as we were getting together, and just to put their technology into perspective here, and Caroline, if you could go to the flow chart. You know, their technology here is all about biogas upgrading and removing sulfur elements from biogas. And if you haven't been to this part of our website, you know, you can go under resources and RNG, and there's this flow chart that we have here for making RNG and biomethane from either digester gas or landfill gas. And we've kind of broken down in a very technology agnostic way the different steps and the different types of technologies that that can be used to clean up your biogas to get it to either pipeline quality or maybe like a medium BTU quality for vehicles. And what we're going to be talking about today is one of the technologies in the orange bar there for removing sulfide related and sulfur related impurities. And as I was talking to the Thiopaq folks, we've got Martin Thiopaq and Andrew Delgado who are going to be speaking to you today, great experts in the field. Their technology really doesn't quite fit into any of these boxes, so we're actually going to need to add another box in here. Their technology is really a chemical scrubber, but with a biological regeneration of the caustic, and they're gonna go through that with you. So you can see we've got lots of different ways for removing siloxanes and sulfides. We're focusing on the sulfide and sulfur elements for today, but that's kind of where they fit. It's kind of chemical and biological there together. One of the nice things is that they don't add oxygen to the gas in the process. So if you're trying to get up to pipeline quality, you don't have to remove that oxygen later to meet your pipeline spec. They've been around for a really long time. They are the original developers of this technology. My understanding is that there are a few other ones that are similar to what they do. They're very proud of the fact they developed the technology originally themselves, and so they're going to be able to speak from that experience with this and lots of different demonstrations, or not even demonstrations, deployments around the world. So we're very grateful to have them as members. We're grateful to be able to have them with you today. And Martin and Andrew, I'm going to turn it over to you all to lead us through the presentation. And as you have questions, anyone, go ahead and put them in the question spot, as Caroline said, and we will handle your Q&A at the end and look forward to getting into that with you. So Martin, thank you, and take it away.
Yeah, hello, everybody. My name is Martin Thiopaq. I'm with Paques, sales manager with Paques. So this webinar will consist of, first of all, an overview of Paques, which I will present. Then Andrew, my colleague, he will get into the details of the Thiopaq process. I will take over again, why to choose Thiopaq. Andrew will present a summary of the engineering and fabrication details of the Thiopaq systems, and then we'll both present the case studies and summarize this webinar, the conclusions of this webinar. I'm gonna turn the camera off now, and then we'll get into the presentation. Next slide, please. So, next slide, please. Paques is a global company. We're big into solving environmental issues, especially wastewater treatment and gas treatment. We were founded in 1960. We got into anaerobic digestion, manure digestion, actually already in the early 70s. But from that grew into anaerobic treatment of industrial wastewater. We're the world leader in that with about 1,500 plants worldwide. That anaerobic treatment is mainly to clean wastewater, not so much about biogas production, but of course those plants also produce biogas. From there we got into the Thiopaq, big into the Thiopaq technology, and well, that's why we're presenting this webinar today. Our head office is in the Netherlands. We have about 100 people there, and roughly 200 people or so in our Shanghai office. Also a large office in Chennai in India, a large office in Piracicaba, and then our office in Burlington, Massachusetts. The company is family owned, but with a 20% share of Mrs. Suzanne Clutton, who is a major shareholder of the BMW company. Next slide, please. We also have a joint venture with Shell. This company is called Paques for desulfurization applications in the oil and gas industry. So we've done maybe 15 projects or so as Paques for also projects in the US and Canada with several oil and gas companies. Next slide, please. Paques is known for its biotechnical solutions of wastewater problems and gas treatment. We always work with natural bacteria, so no genetic modification. In the very early 80s, we got into high rate anaerobic treatment. We developed several technologies since then, making them more efficient and with smaller and smaller footprints, resulting in very slender and tall reactors. And you have to, sometimes people call these reactors also digesters, but they operate at a retention time of several hours instead of weeks, really, for the traditional digester. But remember, these are for industrial applications. Also, we're into ammonia removal from wastewater. That's our Anamox line. It's an alternative to conventional denitrification or nitrification and denitrification. And then, of course, the Thiopaq for hydrosulfide removal from biogas and landfill gas. We also are into other sulfur technologies. For example, we remove sulfate from polluted groundwater or mining effluent, and sometimes we turn, and as part of that, we often actually turn that into hydrogen sulfide to be able to remove it from water. And we often do that by converting it then into elemental sulfur also. Next slide, please. So these are some pictures of our anaerobic reactors. So the USB goes back to all the way to the early 80s, very well-known technology, up to IC reactors, very slender and tall reactors, up to about 90 feet tall. And then nowadays our ICX reactor, which is a follow-up of our IC reactor. And these are used for industrial wastewater treatment. So wastewater that don't contain a lot of solids, but do have a lot of organic material in them. Next slide, please. Paques has invented a lot of its own, or actually most of its own technologies. And we do that in cooperation with universities, several universities in the Netherlands and research institutes. We spend a significant portion of our revenue in R&D, and have, as a result of all this, we've been awarded many awards. The latest big thing that we're working on is production of bioplastics from organic material in wastewater. Next slide. Of course, we're here to talk about hydrogen sulfide removal. So this, probably everybody knows this, but just to capture it. Hydrogen sulfide is very toxic. It's corrosive for equipment, and it gets converted into sulfur dioxide upon combustion. So in most cases where you want to use biogas, or even if you just want to combust it, it needs to be removed to meet environmental regulations or to protect equipment. And well, the norm for pipeline gas quality in North America is it should be less than 4 ppm. Gas engines typically is less than 250 ppm to prevent damage, but it varies a little bit. And some gas engines accept more, or some operators accept more, but it generally results in more maintenance or damage to the engine. And boilers, depending on the type of boiler, it could be that they accept 1,000 ppm, or many times they need less than 500 ppm. Our scrubbers typically take the H2S concentration down to less than 25 ppm. It can be reduced further, but usually it's most cost effective to then polish it with like a media-based system to get it to very low levels. Now we'll get into the Thiopaq process in the next slide, please, and then next one. As Patrick already said, sometimes our Thiopaq is called a biological scrubber, even though we ourselves have been culpable for that. But really, the scrubber itself is really a chemical scrubber, because we use a caustic solution to absorb hydrogen sulfide in the liquid. It's a very dilute solution with a pH of 8 to 8.5, which is highly buffered by bicarbonate, by sodium bicarbonate. So I will describe the process very roughly here, because after this slide, Andrew will continue with the details. But hydrogen sulfide is absorbed in the liquid in the scrubber. This liquid flows by gravity from a sump underneath the scrubber to the bioreactor. in this bioreactor, we have a culture of Thiobacillus bacteria. We add a very controlled amount of air to the bioreactor, and then the Thiobacillus bacteria oxidize the sulfide to elemental sulfur. And Andrew will show that this reaction results in the production of hydroxide. So hydroxide is consumed in the scrubber to absorb H2S, but then it's regenerated in the bioreactor. So it's basically a regenerative system. And the third, and the liquid is now returned back to the scrubber. The slipstream of the liquids from the bioreactor is sent to either a settler or a decanter, depending on how much what the sulfur load to the system is. For larger applications, let's say when it's more than roughly 1,000 pounds sulfur per day, then typically we use a decanter, which adds a bit of cost to the system, of course, but it does also result in an even lower caustic consumption. Altogether, the big advantage of the technology is that it has the high removal efficiency of a chemical scrubber system, but the low operating cost of a biological system because we regenerate caustic. The typical caustic use, depending on the application, is somewhere in the range of half a pound to, let's say, 3/4 of a pound of 100% caustic per pound of sulfur. And that makes this system very attractive. The next slide, please. So the Thiobacillus is a very interesting bacteria. It is a so-called chemolithoautotrophic halotolerant SOB, and SOB stands for sulfur oxidizing bacteria. It's not what you think. A picture is shown in the top corner on the right. There's one bacterium with where you can see how it excretes the elemental sulfur that it forms. And this bacteria is isolated from soda lakes. It's a natural occurring bacteria that can tolerate very high salt concentrations, which occur in the Thiopaq system. And this makes that it can operate at these high salt concentrations, which makes that we have only a very small bleed stream, and it helps in assuring a very low caustic consumption. With this, I'll hand it over to Andrew. He's my colleague, and we'll continue with the process.
Okay, thanks, Martin. Next slide, please. So this is just a basic schematic of the Thiopaq process. As Martin mentioned, it has three main process components. We have a scrubbing tower, a bioreactor, and a settler where the sulfur is removed. So I'm going to drill down into these steps in the subsequent slides here. So next slide, please. So the basic process is that the gas containing the H2S enters into the scrubber section, and as Martin mentioned, it's chemically absorbed into an alkaline liquid stream, and it comes in as it's converted into hydrogen sulfide. So if you can click along here, once the hydrogen sulfide is in solution, it's transferred from the bottom of the sump into the bioreactor. And inside the bioreactor is where the hydrogen sulfide is biologically converted to elemental sulfur. Okay, and then a continuous flow from the bioreactor feeds a settler where the sulfur is allowed to settle by gravity, and then it's removed from the process. So that's the basic process flow, and then I'll break it down a little further here into these three components. So in the scrubber tower it's nothing more than a gas liquid contactor that contains plastic media to provide a high surface area so that the absorption of H2S into the liquid phase happens efficiently. The scrubbing solution rains down from the top of the column, goes through the packing section where the liquid comes into contact with the gas traveling upwards, countercurrent to the liquid stream. The H2S it's absorbed in the liquid stream as hydrogen sulfide, and the treated gas leaves out the top of the scrubber, and the liquid gravity flows to the scrubber sump, then back to the reactor. So as you can see from the reaction, and as Martin mentioned, it operates like a chemical scrubber where it's consuming the alkalinity in that conversion to hydrogen sulfide. Also note here that there is no oxygen that enters into the scrubber during this process at all. The only oxygen is added in the bioreactor, which I'll talk about next. So next slide, please. So the bioreactor is where the bacteria resides and where all the magic happens with this process. So again, the Thiobacillus bacteria, or better known as Theo, converts the hydrogen sulfide into elemental sulfur. So basically, the process is a biological process. The hydrogen sulfide is consumed, and then the elemental sulfur is excreted out of the bacteria. The process is slightly exothermic, so we do need to be mindful of temperature. And there is a heat exchanger inside our equipment container to maintain the proper temperature, which is around 95 degrees Fahrenheit. We also have a blower that provides air at a very precisely controlled rate through diffuser grids that are at the bottom of the bioreactor. We also continuously monitor ORP of the solution, and that provides the control of the airflow of the blower speed. And we also add a proprietary blend of Paques micronutrients to the solution to keep the bacteria happy and the biological conversion predominant, because you can get chemical sulfur formation, and that's undesirable. So we try to keep the optimum conditions for our friend Theo to do what he needs to do. There's also some side reactions that are unavoidable. We are going to get some sulfate production, but by precise control of air, we're able to maintain favorable conditions for biological conversion. Since this is a closed loop process, the conductivity increases mostly through the addition of caustic, and so we have to maintain the desired levels of conductivity by adding fresh water periodically and purging some of the liquid stream, and adding fresh water, and then we have to maintain our proper water levels within the system. We also transfer liquid to the settler, where solids are separated and removed from the process. There is a connection at the top of the bioreactor where vent air is allowed to leave. So you have this air bubbling inside the reactor from the blower. That vent air escapes through the top of the reactor. Usually that stream does not require treatment unless there's some undesirable compounds in there, such as mercaptans, which may necessitate treatment of this stream. But typically for most applications, dairies, manure digesters, we don't need to treat that stream. I also want to point out that the bacteria and the sulfur particles, that they are hydrophilic. We're running at around around 10,000 ppm of solids inside the reactor, and so it all stays in solution. We don't have any problems with plugging because of the nature of these particles. They are hydrophilic, but problems can arise if we're forming too much chemical sulfur through just chemical oxidation of sulfur. That can tend to plug, but by precise control of the process, we're able to maintain favorable conditions in the bioreactor and throughout the scrubber. Okay, next slide, please. As I mentioned earlier, the purpose of the settler is to separate the sulfur particles from the liquid and return the liquid stream back to the bioreactor. A small stream from the bioreactor is continuously transferred to the settler, and the solids just gravity settle to the bottom, and the liquid overflows back to the bioreactor, and thereby we recover the alkalinity that's associated with that liquid stream. Otherwise, we would lose that alkalinity and it would be a waste stream, but that water still has some value, so we want to get it back into the reactor. The sludge at the bottom of the settler is also continuously returned back to the reactor, but occasionally those solids are wasted from the system. The reason we continuously return it is because we want to keep these solids moving, because at the bottom of the settler, we're trying to get around 70% or so of solids, and at those concentrations, the sulfur can start to set up. So we don't recommend wasting to a large tank where the solids can just build up and build up and build up. These solids need to be moving. So for most applications where the sulfur loads are not so heavy, we'll use just a simple cone bottom tank. And other applications where the sulfur load is heavy and we have to manage a lot of solids, we'll use a centrifuge for dewatering. Maybe we can get through this animation. There we go. And then for larger applications, we'll use maybe a centrifuge, and if there's something in between, we may go with a lamella type plate settler to give us good separation. So those kind of in between applications. So as I said, in a settler, we'll typically get 7, maybe 10% concentration of solids. In a decanter or centrifuge type of arrangement, we can get upwards of 60% or so solids concentration. Okay, next slide, please. So as Martin mentioned, we do get a very high performance out of the scrubber. We can get less than 25 ppm H2S. If you want to incur some higher operating costs, when we have some installations where maybe you run at a higher alkalinity than design, and we can get very, very low single digit H2S concentrations. But 25 ppm is generally very doable, and we can provide process guarantees to achieve that. It's a very reliable process with very high uptimes. Besides having a very stable process, we have standard rotating equipment, pumps, blowers, valves, instruments, etc., that need to be maintained. But we do recommend having critical spares on hand for some of the long lead type items in case there's a replacement that may be required. And then, one of the key selling features here is the low operational cost. There's no media to replace. Most of the alkalinity is regenerated, and the sulfur is easy to handle. It can generally be put onto land as a soil amendment, or disposed otherwise as a non-hazardous waste. The other main selling feature is that no air is added to the biogas in this process. So no safety issues are minimized, and you don't need to remove nitrogen or oxygen downstream in your upgrading process, just the CO2. Okay, next slide. So some of the key information that we're looking for when we're designing these systems for you is obviously, we need to know the gas flow. We would like to have average, maximum, and minimum gas flows and H2S concentrations, as well as any special turn down requirements. These systems, they don't have an infinite turn down, so we like to know as much as possible how the flows and loads in your application might fluctuate, throughout the day or through the season or through a startup. So we can design accordingly. Maybe you're collecting gas from a cluster of dairies, and not all the dairies are producing biogas yet, and will be coming online at various times. So that's got good information to know, because we do need to account for low loading conditions at startup, and then as things get online, we can turn things up as needed. Inlet pressure and temperature are also important to know. It's also very important to know if there are any toxicants like VOCs or volatile fatty acids or solids that might be present in the gas stream. So keep in mind, we're often we're the first step in these upgrading processes. We're the first process step. So these scrubbers, they act like a big washing machine. So anything that's in the gas stream, these undesirable compounds, they'll just get washed into the scrubber and end up building up in the bioreactor and start to adversely affect the process. So we deal with these compounds by adding a pretreatment in front of the scrubber, just to do some condensate removal. We may do a little bit of cooling. We're not trying to dry the gas. We just want to cool the gas a little bit, so we can remove any moisture that might be present as a mist, and that mist may contain some VFAs that are carried over from the digester. So we really want to make sure we try to get as much of that out as possible. So we'll put in a knockout tank with a little bit of cooling to do that pretreatment for us. Yeah, it's also important to know the CO2 concentration, so that we can provide a pretty accurate projection of the caustic consumption. And so we do have a process questionnaire that for new applications, so if you fill that out, we pretty much have all the information that we need. So that's pretty much it for the process. Let's see, next slide. Oh, let me just mention real quick here. If I went over that too quickly, if you want to reference, go to YouTube and search for Thiopaq, Paques Thiopaq, and there's a nice little animation video, about 3 or 4 minutes, that kind of goes over the Thiopaq process. Next slide. Okay, so I'll turn it back over to Martin, and he can talk about why you should choose Thiopaq.
Yeah, thanks, Andrew. In addition to you said, I'll also mention that the sulfur that is generated is very pure. It's typically 99% pure, and it can be used as a fertilizer. And Paques is setting up a network to let's say recover sulfur from many facilities, to be able to use it as a fertilizer, so that it doesn't need to be disposed of. So please, next slide, please. So why would you choose Thiopaq scrubber for your desulfurization project? Well, it has first of all, it has a very wide application range, and I'll show that in a few slides down, what the range is. It's a robust and reliable technology. It's been around for almost 30 years. The bacteria, some people don't like biological processes, but all the hydrogen sulfide is produced by bacteria, and there's nothing wrong with removing it with bacteria either. These bacteria live naturally under very tough circumstances, and they're under the circumstances that we apply are very fast growing. And should there be a mishap, these bacteria can actually be stored and survive for months without feeding them, just by setting them inside in totes. And should something go wrong, you can very quickly reseat your bioreactor and start up again. The reliability, our uptime for most plants is 99%. And we can, in certain cases, we can also if certain conditions are met, we can guarantee an uptime. Really no gas or air is added to the gas, so no oxygen. There's no oxygen or nitrogen added to the gas. We can achieve typically more than 99% removal efficiency and less than 25 ppm H2S. It's easy to operate. Typical time needed for daily operation for, let's say, a standard system. And standard is, I'll get to that later, what is a standard? That's typically between half an hour and an hour per day. It consists of taking some samples, some simple tests and some visual observations, and some cleaning and a weekly calibration of the instruments. So that altogether, all that results in very low operating and maintenance requirements, and into a low total cost of ownership. That's the most important point. Low total cost of ownership. If you look at it over more than, let's say, 2 or 3 years of ownership. The capex is higher, for example, than scavenger systems, but the operating cost is much lower. We don't produce hazardous byproducts, and I mentioned the elemental sulfur already, that it can be used as a fertilizer. Actually, it also has some fungicidal properties, but people that use it as a fertilizer see a difference compared to chemical fertilizers, because the elemental sulfur never produce, like what Andrew already mentioned, it's hydrophilic, so it's better soluble in water, and plants seem to take it up better and faster. Then also, it's a very mature technology. In the next slide, it shows the next slide. It shows the number of units installed since the first one. The first one was installed in 1993. By now, a total of 265 has been sold, with about 10 or 15 underway, and a total of approximately 150 metric tons of sulfur per day is removed worldwide. In North America, so US, Canada, and counting Puerto Rico, we have 36 installations. Next slide. So our applications are, in terms of sulfur load, landfill takes up the biggest part of it, because landfills where we have systems, they tend to have very large flows, and sometimes also with very high concentrations. Not always. I mean, they can also have like 700 ppm or so, but they typically have very high flows. The pulp and paper industry, that's where our first one was installed. The gas flows are not as high, but they tend to have like 1% or so hydrogen sulfide in their gas. And then many other applications in the food industry, ethanol industry, chemical industry also, and then digesters. There's not that many in digesters yet, but this is, of course, a very big market now, where all these big dairy digesters that produce biogas, that's a very good application for us. Next slide, please. So where is the Thiopaq applicable? So anywhere where the hydrogen sulfide concentration is more than 500 ppm in gas, I must say, and not in air, because there's just too much oxygen in air. So in gas, more than 500 ppm. When it becomes attractive, it depends on other factors as well, but the minimum load would be about 60 pounds per day. And just to give you an idea, we think we're very, that the total cost of ownership within 3 year time frame or so is less than a media-based system, if you are dealing with a sulfur load of about 150 pounds per day or more. The pressure range is basically, well, we operate some landfills at minus 200 inches water column, and in the oil and gas industry, we have a plant running at 75 bar or 1,000 psi. Yeah, so the bacteria don't really care about this pressure. You know, it's just, of course, the scrubber column has to be designed properly for it. And a typical turn down ratio for our plants is 4:1, but if we know ahead of time that more of a turn down is required, the maximum turn down ratio is a factor of 10. Next slide, please. All right, yeah, then here, oh, well, it's okay. Here you see a number, okay. In the bottom left, you see a small scale scrubber. I think that one was treating something like 50 pounds sulfur per day. And the one to the right is our system at a landfill in Korea, where we treat, this one was sized for about 12 tons a day and almost 20,000 CFM, and the system was doubled up, and it now treats about 20 tons per day sulfur and even higher gas flow. Next one, please. This is a bit of a sample of different size reactors. So a very small one to the left, that's you know, that treats about 50 pounds a day also. The one at the right bottom, that's in the oil and gas application, see it's really a very slender scrubber, so it means it operates at a very high pressure. And the size of plant that is typical for the cow manure application will be the one at the top middle for, let's say, 1,000 pounds a day. Execution there is a little different. What we do for the smaller applications, like the two top ones, the left one and the middle, is that we provide a housing that contains all the equipment, like the pumps, the instrumentation, the PLC, some chemical storage, instrumentation, and it has all the wiring and piping connected inside it, a scrubber and a bioreactor and a settling tank. Those are the major components of the standardized Thiopaqs. If you get into very large sulfur loads or very high flows, then we cannot use these standardized units anymore because the pumps get too big, and many times a decanter is required. So we then do all the process engineering and provide all the process equipment, like all the vessels, the pumps, the heating and cooling equipment, instrumentation, etc., and do the commissioning and startup. Next slide, please. So we already talked about low operating and maintenance requirements. So besides the chemicals, utilities required are we need some makeup water, power, of course, some instrument air, and then for most applications you need either some heating or cooling, but it's not always required. And the waste stream produced for smaller applications, like the typical cow manure application, for example, you get a slurry from the settling tank that has 5 to 10% sulfur in it, plus some salts, and that can be blended with a digestate, for example, or if you have an aerated lagoon, it could be discharged there. For higher loads, the sulfur can be that is taken from the bioreactor, is sent to decanter, and it can be concentrated up to 55 or 60% solids, and that sulfur can be recovered and used. So it's of a high quality, and through a company, a Paques-owned company called Thiopaq, we can take off this sulfur and so that you don't have to dispose of it. Then this, I already mentioned the sampling and testing requirement, and then the general equipment maintenance. But this is usually combined with other maintenance on other components of the plants, and typically no more than 1 or 2 days a year should be needed for like major preventative maintenance. Next slide, please. Yeah, so what are the, I wanted to get into everything here, but I would say the major advantages, if you summarize it, is we have a reliable system that provides a high uptime. There are unfortunately also some copycats. There's several companies in the U.S. and also outside, in Europe and China, everywhere that copy these systems, but often the fundamental knowledge is not there to guarantee a very reliable system. And if you have any amount of downtime, it gets very costly if you produce RNG. So I think we have a big advantage there. And the cost of ownership, the total cost of ownership, including CapEx and operating costs, are among the lowest you can get if you're above a certain sulfur load. And I would say generally that is above under 50 pounds sulfur per day against pretty much any technology. And below that, we can be competitive against media systems, down to maybe about 60 pounds per day or so. And then, it's very flexible. Also, it can treat very wide fluctuations in gas flow and sulfur load. I'll hand it over to Andrew again for the next slide for the engineering and fabrication aspects.
Okay, thanks, Martin. Next slide, please. So I wanted to make a couple of points that maybe I glossed over before. And as Martin mentioned, we have several sizes. There's some standard sizes, but there's also multiple configurations. Generally, so the scrubber, the diameter of the scrubber is determined by the gas flow. So the more gas flow you have, the bigger diameter you have. The bioreactor is designed based on the loading. Okay, so if you have a lot of pounds of sulfur coming in on a daily basis, the bioreactor is bigger, the blower is bigger. But there's some cases where we can have multiple configurations. You'll see in some of the case studies, you can have 2 trains, you can have a scrubber with 2 bioreactors, you can have 2 scrubbers with 1 bioreactor. There's really an endless way to configure these things to meet the requirements of the project. As far as engineering and fabrication, so with Paques, you get a complete comprehensive engineering package with our projects. So we do a complete mass and energy balance. We have a process flow diagram with stream numbers, and each of those stream numbers gives you the constituents of that stream, and you can see how things change as you flow through the process. So that's valuable information, when you're integrating these RNG, upgrading projects. Of course, we do P&IDs complete with, line sizes, materials, all the instrumentation, pumps, and everything's shown there, just as you would expect. General arrangement drawings will provide a site plan showing the arrangement of the equipment. We also will provide individual arrangement drawings of the various pieces of equipment, the scrubber, the bioreactor. You can see in that picture the container, which is the module that houses the equipment. And then in the upper left-hand corner is the sodium hydroxide bulk storage tank. We can also do piping isometrics, 3D models. Sometimes our orders, will come from engineering companies where, they're capable to do that, and that's fine. We're very flexible to, arrange our scope to fit, who our customer is. We do all the electrical schematics for our system. So even though most devices are installed inside the container, there may be some control valves, some level instruments, some other pressure transmitters that are external to the container. So we do, single line electrical drawings for the complete installation. We also provide all the detailed submittals, equipment data, instrument data, that sort of stuff, as well as an O&M manual for you to reference, going forward. Next slide. So the tanks are typically made of fiberglass or HDPE. And some of these higher pressure applications or vacuum applications, of course, we'll probably need to go to a different material like stainless steel. But the majority of applications that we're seeing, in landfills and dairies, they're at relatively, low pressures and operating that pressure, not at vacuum. As I mentioned, the equipment is pre-installed inside a 20-foot high cube container. It's completely, renovated. Everything's insulated. The walls, the ceiling are insulated. A steel floor is put in. We have HVAC, ventilation fan, air conditioning, heating, lighting. We have a man door on the side. So all the major equipment is installed in here, to the maximum extent. And we use, major equipment that, you're used to seeing, that you'd expect in this kind of an installation, Gould pumps or Fibroc, Anderson Hauser instruments, that sort of stuff. So readily available parts. Next slide, please. As far as the controls, it's a fully automated process, PLC controlled. All the electronics are installed in a UL 508A panel. We use a Compact Logix Allen Bradley PLC with an HMI interface where all the operator, functionality takes place. There's data trending where we can look at, key variables and how they change maybe over a 24-hour period. So it's a very nice interactive display to give you, the operator, the data that he needs and the ability to control everything that needs to be done. We also have the ability, and we like to get a VPN connection. We have a network switch inside the panel where we can get, if we get set up with a VPN, we're able to remotely, access the controls. And if you get into a pickle, we can quickly respond and make whatever changes, help with troubleshooting, see what you're seeing in the field, and get you back on your way. Next slide. Okay, so now we're gonna go over some case studies and I'll flip it back over to Martin.
Next slide, please. Yeah, I'll briefly discuss two case studies. First, this one, I selected this one for two reasons. First of all, because it's our first plant that was built in 1993, and it's still in operation and doing well. Something else makes this plant, or this plant, very interesting as well, is that it treats the biogas from anaerobic reactor, I should say, that treats effluent from three separate paper mill companies. So it sees a lot of variations in flow from these mills, because they can, all of a sudden dump a lot of water and then nothing, and so on. And also variations in gas flow composition. don't forget that these anaerobic reactors, they work at retention times of, well, this one probably, I'd say somewhere around 6 to 10 hours or something. So gas productions can change dramatically within an hour. So on this slide, you see the Thiopaq. You see the entire treatment plant. So the anaerobic reactor is kind of in the center with the white covers there. And the Thiopaq is located nearby. It's kind of hard to see, but it's in one of the next slides. So next slide, please. So the name of that company is Industry Water. Here you see the results of the last 11 years of operation. You see that the influent gas concentration varies typically between 5,000 and 10,000 ppm, and the outgoing concentration is generally less than 50 ppm. You see over 11 years of operation, you just see a few hiccups, just indicating how stable this process has been working. Next slide. And this is a slide of the daily, this is just one day of operation, and you see how at highly variable gas flows from the gas flows here in cubic meters per hour. So they vary from 250 to 750 cubic meters an hour. So I'd say roughly 150 CFM to just shy of 500 CFM. They vary all over the place, and it doesn't have much impact on the outgoing hydrogen sulfide concentration. Next slide. So this is the older Thiopaq. So back then it was done a little different. You see the scrubber, obviously the tall structure, and a building with the equipment, but it wasn't a modular building yet. And then the bioreactor is the rectangular building next to it. Nowadays it's done very differently. The uptime of this facility has been 99%. The average removal efficiency is 99.7%. The average caustic use has been half a pound of 100% sodium hydroxide per pound of sulfur removed. Next slide, please. This is a different plant, one of our more recent installs. This is at a landfill in Quebec. This plant was started up sometime April last year. So it's been in operation for a little over a year. It was designed for 6,000 CFM and operating. It's treating all the gas, but it's getting on average a little less than that. These are average numbers. The numbers there are average for the year, the last year of operation. Hydrogen sulfide going in is 771 ppm on average. The design number was, I believe it was 1300 ppm, so it's a little lower than design. We designed it to achieve less than 25 ppm. It's a number that we guaranteed. The actual number was 0.5 ppm, or less than 0.5, so I rounded it off to 0. The sulfur load is 530 pounds per day, and at this plant we have a decanter to dry the sulfur. So the scrubber you see in the forefront, it's a 80-foot tall scrubber, and it's 10-foot diameter. And there's a inlet knockout tank in front of that, and the outlet knockout tank. Bioreactor was partially installed inside an existing building that's kind of right behind the scrubber. So the tank behind it sticks out. It's sitting on the bottom. It's sticking out through the roof. and all the process equipment is installed in that building. And there's ample space there. There was just a building that wasn't used anymore. Then I think that's it for me. I'll hand it over to Andrew again. Sorry, here is some more data. This is the operational data for the last year. So you see the gray line is the gas flow. So it's very generally close to 6,000 CFM. The inlet gas concentration has slightly declined over the year. In the beginning it was a little higher, but it's now, it's average 770 ppm. And out is basically, nothing. Andrew, your turn again.
Okay, next slide, please. So this is we have a Thiopaq installation at a large rum distillery in Puerto Rico that we recently commissioned about a year or so ago. It's already weathered a couple of hurricanes. It's still standing and is operating pretty well. In this project, the treated gas is used as a fuel source for the distillery's boilers, and it saves them quite a bit of money on fuel for their boilers. As you can see, the loading on this system is quite high. It's designed to treat about 3,000 SCFM with H2S concentrations of around 17,000. The system was installed to replace a iron chelating type system where the customer was having issues with plugging due to high sulfur concentrations and just kind of general solids management. They had two large plate and frame filter presses that was just taking a lot of labor and just general, higher than expected operating costs and just general difficulty managing the process. So we came in and replace that system with a Thiopaq process. The distillery operates in a campaign mode where they'll operate continuously for about 3 months, and then they shut down for about 2 weeks. And during those 2 weeks, they have very, very minimal gas flow. So we took that into consideration when we configured this system. We went to a dual train system. Like I mentioned before, we can configure these and multiple configurations to meet the requirements. So having two 50% trains, it gives some redundancy as well as operational flexibility to better manage those operating cycles. Okay, next slide. This is an installation in Oregon at a large dairy manure. I think there's around 20 or 25,000 head of cattle. We're treating about 1,800 CFM of gas. H2S concentration is 2,000 ppm. A sulfur load of about 300 pounds per day. And this is the first step in the upgrading process. There is an amine process provided by Pure Gas, Wärtsilä Pure Gas, downstream of this system. And then there's moisture removal, and then the system goes on to pipeline injection. Next slide, please. So here's some data. As you can see, kind of typical of the data that Martin showed. We get very high removal efficiency, gas flow, and H2S concentration. Somewhat variable, a little bit seasonal. As the warmer months change into colder months, you get a little bit of variation in H2S concentration, but all the time we're maintaining a very low effluent H2S. Next slide. Another dairy in Idaho. This is an RNG upgrading plant. Similar as to Oregon, a little bit smaller, 950 CFM, H2S around 3,000, outlet H2S 25 ppm as well. So again, this is an upgrading process, and downstream of the Paques system, we have there's an air liquide membrane process for CO2 removal. And then in the next slide, we can see some data. Basically, again, very, very stable effluent H2S, very stable H2S removal here. So I think that's it for me. I'll send it back to Martin, and we'll get this summarized and wrap up.
Yeah, so summarizing, well, the Thiopaq scrubber has been around quite a while, and it's been a proven and reliable process to remove hydrosulfides from biogas, landfill gas, and other gases. It's applicable to a wide range of gas flows and sulfur loads, and it has a low O&M cost and low total cost of ownership. And what distinguishes us from some other companies is that we have a long track record for the developers of this process with 30-year experience, and we have to know how to properly design a system, and the experience in-house and in North America to prevent problems, execute projects, and we can provide technical support should that be needed on very short notice. And thank you for your attention. I'll hand it over to Patrick for a question and answer session.
Thank you so much, Martin and Andrew. That was really great. I learned a lot about your system here. We've got about a dozen questions here, which is great to see. So let's try to run through them. I'm going to group a couple of them that are similar, and if any of the rest of you have questions, please go ahead and enter them in, and we'll get to them here. I know we're kind of scheduled to end at the top of the hour here, but if you need to leave, you can. We hope that you'll stick around. This is being recorded, so we're going to try to answer as many of these questions as we can, and so you'll have those in the recording. And of course, Martin and Andrew are available to you, and would love to follow up with you for any questions or further follow-up that you all have. One of the first questions here has to do with the maximum amount of H2S you can remove from a gas flow. I saw your Puerto Rico project had about 17,000 ppm. One of these people is asking specifically if you can handle 25,000 to 40,000 ppm of H2S. What's the limit, maybe a functional limit of your system?
I think we can go up to 99% or so. The only thing is we need some carbon dioxide for the bacteria to grow, but we can treat much higher concentrations because the bacteria don't actually see those high concentrations. The bacteria, the equilibrium concentration of sulfide in the bioreactor is close to zero because the bacteria remove it so efficiently. So you can take pretty much any hydrosulfide concentration.
Great. What kind of control equipment is used to maintain the temperature and chemical levels in the bioreactor?
So we have a temperature frame heat exchanger to control the temperature. So we'll need hot water and cold water. So we have dual direction control, and we just have a modulating control valve to maintain that temperature. And I think the other part of the question was chemicals. So generally the caustic is controlled on, we have a pH meter, but it's really, we look at the pH and we also measure alkalinity, on a daily basis and make sure our alkalinity is good. The nutrients are dosed on a pulse pause type of a arrangement. So it's fairly simplified control.
All right. What ORP levels do you recommend for the biological reactor, and how much salinity or sodium concentration is allowable in this chamber?
For most applications, it's around minus 350 to minus 380 millivolts redox potential, and the sodium concentration Well, I don't know the number offhand, but I think it's up to, I believe it's up to 1 mole per liter. So that would be about, what would that be? About 25 grams sodium per liter, something like that.
The conductivity will be typically in the range of, say, 40 to 80 millisiemens per centimeter.
We've got some questions here about what other constituents your system might remove. One person's asking if you remove any CO2 during the scrubbing. Obviously, you need some of the CO2, as you explained, and also are siloxanes captured by the scrubber. How do you handle those constituents?
Yeah, we remove a few percentage points of CO2 that get absorbed and then stripped out of the bioreactor. And siloxane, we don't really remove it, but also it doesn't bother us. I think it all stays in the gas.
So for a dairy biogas project, this person's writing at about 500 SCFM, standard cubic feet per minute, with, let's say, 4,000 ppm of H2S. What might be expected for a range of oxygen post-treatment for a digester that does not introduce air into the digester? So very specific question that you might want to follow up with afterwards, but do you have anything off the top of your head to be able to respond to that?
So I didn't
well, we don't.
That. Oxygen.
Well,
Go ahead, Martin.
Yeah, I'm not sure either, but I think, well, we don't add oxygen to the gas, and the oxygen that is there, probably some of that would be removed. I mean, you could get some uptake of the oxygen in the liquid in the scrubber, but I'm not sure if that answers the question.
Thanks. We'll let you follow up afterwards, but it sounds like the oxygen concentration is probably going to be just a little bit less than whatever it was that came in the first place.
Yes.
What about the gas flow and H2S composition on the first installed project shown? And now I'm looking back to your slides to see which was the first installed project that you referenced there.
Yeah, that was the one in 1993 at the paper mill. And what was the question?
What
was oxygen concentration?
What was the gas flow and the H2S concentration?
Oh, the gas flow, it varied between 150 and 500 CFM. And the H2S was between 5,000 and 10,000 ppm going in.
We've got a question here on sulfur as a fertilizer, and we've still got them pouring in here, so it's great. I know several of you had to go, but we've still got a lot of folks on the line asking questions, so that's great. Sulfur as a fertilizer, how can folks get more information on that?
They should they can contact me, Martin.
Okay, we'll make sure, if it's not already, we'll make sure that your contact information's in the email that we send out to everyone with the recording and the slides. You'll all have access to that. What if someone produces pure biomethane directly from the digester process? It would make your technology obsolete, right? Well, I think we would probably answer that one. Yeah, if you didn't have any impurities that you needed to remove, you wouldn't need any gas upgrading systems of any kind, whether it be yours or anyone else's, right?
Yeah, that'd be nice, but it's impossible though. I mean, you always produce CO2, and if you need to have sulfate because it's a nutrient as well, the sulfur. So you always have some hydrogen sulfide in there. So yeah, I think you'll always have to remove CO2.
We've got a cost question in here, and I'll let you decide how you want to answer it. But it's for a dairy biogas system in the range of 600 to 700 SCFM. Any kind of a ballpark range of price that you'd like to quote on that?
Well, also we don't know the hydrogen sulfide concentrations and what our scope exactly would be. So, and yeah, no, they can contact us, and we always send a questionnaire to people in order to work up a budget quote. So we definitely need to have more information.
Is there any benefit to operating at higher pressures versus lower pressures?
Yeah, depends how you define high and low, but you know, if you work at, let's say, low at a vacuum, it makes your scrubber larger, and it can require some extra safety equipment and process control equipment. High pressures also may get you, but if you call high, like you know, the typical range, if you stay under 10 psi, then there really, for the process, there isn't that much difference. I mean, sometimes a change can just push it into a larger or smaller scrubber or so, but we cannot generalize that.
What kind of maintenance is required for the packing, and you know, what kind of frequency do you need to do that maintenance?
For the packing, so the scrubber, only the scrubber column has packing in it, and there's really there shouldn't be any maintenance required. But what can happen is that if you operate it under the wrong conditions, that you can get chemical sulfur produced, and that can coat the media, and then you have to clean them or replace them. But it's something that can be avoided. So it's not typical to do maintenance on the scrubber media, other than, you know, an inspection during an annual or 6-month inspection. You would inspect the top of the media and check that the spray pattern is also correct, and check for fouling. But that's all that's done.
And we have delta P. We monitor pressure at the bottom of the packing and at the top of the packing. So if it is starting to plug, you know, we'll get some indication by seeing a larger delta P. But typically the delta P on a clean packing is very low. It might only be a couple inches of water. So obviously, if you see the trends start to increase, then, you know, maybe there's you know, more chemical sulfur. There may be some plugging starting to happen, so you can get ahead of it.
Great. What about other sulfides other than H2S, like methyl mercaptan, dimethyl sulfide? Do you remove any of those other sulfides?
No, we really never measure them either, but we don't think that they are removed. These bacteria don't remove them, as far as we know. So, and also we don't know how much gets absorbed in the scrubber, so we really don't know. So we don't. There's certainly no guarantees on that. And too high concentrations. The concentrations are really high. That's all. That could be problematic for bacteria, because it's you could get growth of different bacteria in the bioreactor, and that's what we want to avoid. So there's a limit. There's an upper limit to the amount of mercaptans that we can accept, and you know, we don't know how much is removed.
So this is a question about iron sponge systems. So different kinds of sulfur removing systems. Where would the Thiopaq system have an advantage over iron sponge for smaller systems? Or, you know, is there some kind of a crossover, a threshold where one maybe the Thiopaq system makes more sense and an iron sponge makes sense in another situation?
Well, I think if you look at it over long term, that definitely benefits the Thiopaq, because you know, you make a one-time investment in a Thiopaq, and then you have continuously low operating costs. So I think if you're at a sulfur load of 200 pounds per day or so, that the payback will be compared to a similar sized iron sponge system, that the payback will be 2 years and maybe less. And if you're at the other end of the spectrum, like let's say 60 pounds, if that's the average load, then I think you're probably more looking at like 10 years or so. But of course, you also avoid the hassle of every so often, every 6 months or so, having to dispose of the material and having to deal with that. And instead of that, you would have a continuous operation.
So this is a question about the Canadian project you mentioned, and you mentioned that you use a decanter. Was it a decanter or a centrifugal decanter?
The centrifuge, yeah, it's really they're the same thing, but I think decanter is more word used in the wastewater treatment, which is kind of this is, and I think a centrifuge could be different configurations, and I believe they run at higher RPMs. With the, so a decanter is a type of centrifuge. That's how you can say it.
Okay.
But meant for higher flows, I think.
If you wanted to get below 4 ppm H2S concentration, would you just have a taller scrubber system, or would you use multiple scrubbers?
Yeah, typically with getting down that low, in these upgrading process, you're going to want to have some kind of scavenger media, downstream to polish. But the workhorse is going to be the Thiopaq. You're going to have very, very low cost operating costs with a media system that can guarantee you that 4 ppm for your pipeline quality all the time. So in general, these upgrading systems will have some sort of a scavenger downstream.
Got it.
Yeah,
go ahead.
It's possible to do that, but it doesn't make economic sense anymore to do that, because your scrubber would have to be higher most likely, and you're going to use more caustic. So your caustic use goes up and your power cost goes up. So to remove those last few pounds of sulfur really increases your operating cost. It's just better to put in a polishing system for that last little amount.
So this is a question about the limit on CO2 concentration. Is there a limit? And I'm guessing the question is there a lower limit for CO2?
Yes, there is a lower limit. I'm not sure exactly what that number is, but there is, yes, because you need some carbon for the bacteria to grow. And upper limit also there because if your CO2 to hydrogen sulfide ratio becomes very high, then your caustic use per pound of hydrogen sulfide, that number would increase as well. So, but definitely up to like, and usually, I mean, biogas and landfill gas typically don't have more than 50% or some have 60% CO2, but that is not a problem.
Great. And just for those of you listening in here and noticing that, it's now 20-some minutes past the hour, we're going to go to the bottom of the hour, so 30 minutes after the hour here, so 7 more minutes here. There's so many questions here that I haven't even counted them all. I think there's at least still 20 left, and from many of you. So, many of you are engaged in asking questions. What I'll tell you is we're going to answer as many as we can in the next 6-7 minutes here. And Martin and Andrew will have all of your questions in a report that we give them right after this. So we can follow up. They will be able to follow up with you, or you can follow up with them with the contact information we'll give you for any that we don't get to. But let's see how many more we can get to here for all of your benefit. What pH level is required in the biological stage, and how expensive is the oh gosh, I should know my compositions here. NaOH, so that's sodium hydroxide consumption.
Yep.
Yeah, so generally we're using, well, pH is, around 8.2. The sodium hydroxide concentration that we use, I mean, with these chemicals, you're depending on where you're located, the cost there is in the transportation. So the higher concentration, the better. We design our systems to take 50% sodium hydroxide. So as I mentioned before, There's a double-walled sodium hydroxide tank, typically in our scope. It's got insulation and heat tracing, so it keeps that sodium hydroxide solution, nice and warm, because it will freeze at temperatures of less than 56 degrees, I think, Fahrenheit. So yeah, 50% sodium hydroxide is what we'll use.
Great. So this question is about wastewater coming from the process. Is there any, and what characteristics does it have? The question is, I understand that you reuse the liquid from the bioreactor in the scrubber and require some amount of makeup water. So, at the end, is there any wastewater from the process that has to be dealt with? And if so, what kind of characteristics does it have?
Yeah, so if you kind of go back to the slides that, on the process, think back there, the sulfur has to go somewhere. So there is that solid waste stream from the sulfur settler, or if you're running a centrifuge, you have the sludge cake. That's where the sulfur is. It's got to go somewhere. It's either going to come out in a thick, 10% slurry, or come out in a sludge cake. So that's one stream. And then there's going to be a bleed stream as well to kind of maintain the conductivity. So there'll be kind of a dilute liquid stream, and that sludge cake stream. So
this question goes back to the polisher, and they don't recall seeing an H2S polisher in your flow diagram. So do you typically use a polisher? Andrew, I know you kind of referenced this a little bit earlier. Do you typically use a polisher for RNG applications? And if so, what kind of a polisher do you like to use?
Yeah, normally our scope will end, right at the discharge of the scrubber. Maybe we'll put it in an outlet knockout tank like the Canadian landfill that Martin talked about. But as far as a scavenger media system, we normally don't provide that. It'll be by others.
Great. How is the elemental sulfur separated from the biomass in the settler?
Just by gravity. It's just a gravity separator. That's it. So nothing fancy about it. Like I said, a cone bottom tank. Just the velocity slows down, and it just settles by gravity, whether it's a cone bottom tank or a lamella type separator.
So going back to the sodium hydroxide here, how much of the sodium hydroxide reacts with the CO2? And someone else also kind of asked a similar question here. How does the CO2 content affect the sodium hydroxide consumption? So kind of I guess they're asking about the interaction there of those two compounds, the carbon dioxide and the sodium hydroxide.
Yeah, unlike a caustic scrubber where you absorb, where a lot of the caustic is spent on absorbing or reacting with carbon dioxide, here we don't. The caustic use is more due to the fact that we produce some oxidized sulfur like sulfate and thiosulfate, and because we have to dispose of some bleed, rather than that a lot goes to absorption of carbon dioxide. This is because of the pH that we work at. The pH is only 8 to 8.5 at the most, compared to a caustic scrubber that works at a pH of 11 or 12 or so. So that's why we don't absorb much carbon dioxide.
Great. And I think we'll do one last question here. So let's see. This goes back to the bacteria and other constituents. So you talked about, the fact that there's not much data on other sulfides being removed, but this question's slightly different. What potential constituents in the gas can be toxic to the bacteria? Can the bacteria handle other organosulfur compounds, or any of these compounds removed? So I guess you've already answered that question about other sulfur-related compounds being removed, but are there any constituents in the gas that can be toxic to the bacteria?
there can be things that there are things that can be toxic that that are toxic for many bacteria, but it's rare, very rare for us to run into that. It could happen, I guess, at landfills. That's why we ask for the VOC composition. That like BTEX, for example, benzene, toluene, xylene, those kind of things, cyanide. High concentrations of ammonia, but it's not something. So if there's something that obvious in the screening process for us, in a questionnaire we ask for those things. Regular digesters, you'll never run into those things except ammonia. Some digesters could have high concentrations of ammonia. These other things you never run into that unless maybe a landfill, and even there, I don't recall having toxicity problems even at landfills. So, but it's theoretically possible, yes.
Great. Well, thank you, Martin and Andrew. I do see that there's some follow-up questions that folks have had even to some of the answers here. And so, you've clearly piqued the interest of a lot of folks. We had a couple hundred people attend today, which is fantastic. I hope that you all will be able to engage with each other here after this event, and that you've all learned something new that you can use for your business. That at the end of the day, that's what the American Biogas Council really wants here, is for more biogas business to happen. We want to see more biogas systems built and more equipment sold, and you have a chance to do that now, even more so with some of the information that you received today. So thank you all for attending. I do want to remind you that we are going to have a few other virtual events coming up with the American Biogas Council, so look out for your email for announcements of those. And as soon as you sign off today, a survey, a really short survey, it's just a couple questions, will pop up. We actually do use the answers for these surveys for our events. That's really important to us. So it'll only take you probably less than 2 minutes. Just answer them real quick. Basically, did you like the webinar? What did you like? What didn't you like? So take a look at that. Please fill it out. And if you're not a member, please think about joining the American Biogas Council, and hope you all can do some business with Paques. Thanks so much for attending. Thank you, Andrew and Martin, and we'll talk to y'all later. Bye now.
Thank you very much, Patrick and Caroline.
Thanks everybody for your attention.
Thank you.